Is that all right with you if I record this?
Go for it.
Cool. Um, just a quick rundown of what I considered a pretty difficult problem. The exam will be a lot shorter than this. None of the questions will be quite this long, but it covers a lot of different things. So we're doing a quick overview of nomenclature. We have H3PO4. I'm identifying first the polyatomic ion. I know that this is an acid because of the hydrogens here, and we want to find the polyatomic ion name on our chart that's always given to us on the exams. So this would be phosphate, and so I'm going to write down phosphate. Now, to convert this into the polyatomic acid name, you got to remember that just a small trick here that 8 always becomes ic, and ite always becomes us, O-U-S. And so since this is phosphate, I'm going to drop the 8 and replace it with ic. So this becomes phosphoric. Unfortunately, there's a little bit of a trick that goes into remembering whether it includes the like a longer version of the element name. There's no easy rule other than practice for those, but I am going to go back and give partial credit for those on the exam. So make sure you're just showing your work, write things out as well as you can. This would be phosphoric, and then of course acid at the end because we always want people to know if what they're handling is an acid. So this would be phosphoric acid. The next compound that we had there was Na2CO3. So this is going to be a different type of compound. It's not starting with a hydrogen here, so we know it's not an acid. That leaves two different types. We either have either ionic compounds or we have molecular compounds. Ionic compounds will always contain a metal. The molecular ones will never contain a metal. So it really helps if you remember from your periodic table where that kind of stair-step division is between the metals and the non-metals. Sodium is a metal. And so we can name this compound using ionic nomenclature. I also notice that there's not just two elements here. We have three different elements. You can tell that it's three elements because of where we used capital and lowercase letters. Every capital letter indicates the beginning of a new element name. And so sodium, Na, and then the next element over, C is for carbon, and then the capital O tells us it's oxygen. One of these things must be a polyatomic ion. Only nonmetals can form polyatomic ions, and so the CO3 must be our polyatomic ion. You're going to want to look at that same polyatomic ion reference sheet you get on the exam, and you'd find that that polyatomic ion is carbonate. So we have some sodium here, and we have some carbonate. And it turns out that for naming the ionic compounds, since they have predetermined charges, you don't need to worry about any prefixes or anything like that. This would just be called sodium carbonate as is. Next, we had Na3PO4. William, you want to try doing that one?
Okay. N-A. Can you write it down?
You
Sorry.
got it.
PO4. So PO4 is my polyatomic ion.
Hmm.
And then I don't have a list in front of me.
We've already used that polyatomic
Oh,
ion
sorry, it's
name,
phosphate, so it becomes eight becomes ic.
but that's only if we're naming an acid, right?
Oh, that's right. So then it would just become sodium phosphate
Yep, that's it.
because it is an ionic.
That's right. Good stuff. Okay. We also have one remaining type of nomenclature, which was the molecular or covalent nomenclature. So I see that we have a CO2 there. Let's go ahead and name that one. Of course, you probably are familiar with what CO2 is called at this point in your academic careers. I feel like it kind of just it makes its way in through osmosis. We hear about it enough. CO2. But let's go ahead and apply the rules to this. We know this is molecular because it's just two nonmetals attached to each other. With
Mm,
the nonmetals, they can form a variety of different valences. You can have one atom, two atoms, two and four atoms. It can get really quite complex. And so we use Greek prefixes in order to specify how many of a particular atom are attached in this particular naming scheme. When it comes to the first atom, you don't need to add anything to it as long as there's only one of them. It's kind of redundant. We assume that if there's just one, then you're just calling it the element name. And so we would just call this carbon. And then you got to figure out how many of this other element we have. There's two of them. So di is the Greek prefix there. And then oxygen becomes oxide. In general, when you're doing molecular nomenclature, you're going to drop the end of the element and replace it with IDE. And so there, that's carbon dioxide. Let's do another one of those just for practice. Let's say we had something like, hmm, P2, oh, whoops, O5. So here you would want to figure out the two elements. William, you want to walk me through this one?
sure. I don't have a periodic table in front of me,
P
so
is phosphorus.
well, I know that, but the types that they are.
Ah, okay. These are both nonmetals.
Okay, so that means they're the what's it called? The third one.
Yeah,
Not
molecular.
ionic. Molecular, thank you. So then it's gonna be phosphorus, and I believe five is pentoxide.
Yeah. Now, how many phosphoruses did we have here? Was it one?
We had five. Oh, sorry, two.
Right. And so because we had more than one phosphorus, we do need to alert our audience to that fact. So this would in fact be diphosphorus pentoxide.
Okay,
So
got
just
it.
make sure that unless the first one is a one, you do need to include the number of that element.
Roger, Roger.
All right, good stuff. Okay, that was just a brief overview of the nomenclature. Let's get into the meat of this problem now. If we have that many grams of sodium carbonate react with 13 milliliters of 1.015 molar phosphoric acid, what is the theoretical yield? So when we're asked about theoretical yield, but we are given two different quantities, we shouldn't assume that those are going to react in a one-to-one perfect ratio. This is going to be a limiting reagent type problem. So we're going to need to calculate how much of each we can, or sorry, how much each one of those two materials will produce for one of the products. And then from there, we're going to go back and do the calculation only using that as our limiting reagent to eventually get to the percent yield. I'm looking at my chemical equation up top, though. Do you think that that is balanced, William?
I'm gonna say no.
Yeah, that's a pretty good call there. Let's go ahead and balance it then. Do you want me to just walk through this, or do you want to be involved?
I'll be involved, sure.
Go for it.
Okay, I know that we're supposed to um save the oxygens for last, right?
Generally speaking, that's not a bad plan. Something else that I would like to point out, though, is that polyatomic ions, like the phosphate here, you can treat those as one unit. Like it's not going to split apart because we have a PO4 on one side and a PO4 on the other. And so don't include that with any oxygen math you do.
Okay. Okay. So mm, 2, 4. So I guess I'd want to my sodiums are not even.
Good call. So we got
Um,
two there and three there. Um, they are not evenly divisible. Remember, no half elements allowed. So
mhm.
what's the next best plan for making these even?
Um, I want to multiply it now.
Yeah.
Um,
Maybe
okay.
maybe a three and a two?
Yep, 3 and 2 sounds great.
Yeah, because that way that we'll get six of each of those, right?
Mm-hmm.
And so from there, what I can do is I'm going to propagate that change that we made to all of the other compounds here. I'm going to start with the 3Na2 and then the CO3s. So the six sodiums here, 3 times 2, matches the 2 times 3, six sodiums on that side. My number of carbons has changed. I have 3 carbons on the reactant side, so I need to put a 3 in front of the CO2. Does that make sense?
Yes.
Cool. And then from there, the oxygens, let's just check. So we're going to exclude phosphate from the math here because that's going to act like its own individual unit. I'm really concerned about whether the 9 oxygens we have from the carbonate manifests over here in the CO2 and H2O. So 3 times 3 gives me 9 on the reactant side. 3 times 2 gives me 6 there. And then I'll also need a 3 right here to get up to 9 oxygens. Did that track? So 3 times 2 gives me 6 oxygens right there. And then 3 times 1 gives me 3 oxygens right there. I
Yes.
take the 3 times 3 there, that's 9 oxygens. And so I think that my oxygens are all set now. Okay.
I follow.
Now, what else have we done here? So I've taken care of the modifications we made from the 3 coefficient on the reactant side. I haven't taken into consideration the 2 we put on the product side there. So 2 times 3, 3 times 2, the sodiums are good. What about the phosphates? So 2 times 1 phosphate. Remember, we're treating this as a total unit here, like one piece. And so instead of worrying about it being 2 phosphoruses and 8 oxygens, just think of it as one thing, and we have 2 of that one thing now. So in order to make that match on the reactant side, what should I do?
I need to multiply on the reactant side now by
Hmm.
2.
You got it. If I put a 2 here, 2 PO4s matches the 2 PO4s. The last thing we need to consider is the hydrogen. 2 times 3 gives me 6 hydrogens. 3 times 2 gives me 6 hydrogens. So I think that we've balanced this equation now. Any questions?
No.
Okay, cool. Now we get to do the fun part of finding the limiting reagent. Let's see. In order to find the limiting reagent, we want to set up two kind of parallel calculations where we're trying to figure out how much of something we've produced. Now, if I had not written this problem on the fly, I probably would have remembered to specify one of the products. So we're going to say, what is the theoretical yield of CO2?
Awesome.
And so that's what we're going to turn both of the reactants into. We're going to be converting them into CO2, and we're going to see which one produces less CO2. Because that's how things work in reality. Everything's always worse than you want it to be. We're going to take the 15.5 grams of Na2CO3. And William, do you have access to a periodic table?
I can pull one up on the Google.
Could you please? Because I don't want to have to leave this page. It apparently doesn't save my writing as I go through. Um,
Yes.
and then I'm going to have you calculate these molecular masses for me, please.
I gotta pull up a good periodic table. One that gives me that.
Yeah, yeah, yeah. I mean, don't they all?
Not the one that I just looked up.
That's funny. What a useless table.
It
Like
had
the
the
whole point
atomic
is to find the.
numbers, but not the mass.
That is wild. Okay.
Okay, go for it.
All right. We have sodium.
Sodium is 22.9.
Thank you. And the carbon is 12 and the oxygen is 16, give or take, right?
Give or take.
Yep. Times 2 times one of those, and we had 3 of those. And so this is going to be the molar mass for my sodium carbonate. I've got a calculator here. I'm just going to plug and chug real quick. 22.9 times 2 plus 12 plus the quantity 16 times 3. And I got 105.8 as my molar mass for sodium carbonate. And of course, that's in terms of grams per mole. This is a conversion factor. We're going to use that conversion factor to change this into moles. If you ever get stuck doing a dimensional analysis problem,
Put
just try and turn it into moles. It usually helps. Now, 1 mole on the top, we've got 105.8 grams on the bottom. And so grams will cancel with grams, tell us how many moles of that we have. Now, I've got moles of sodium carbonate, but I don't really want that. What I want is the amount of CO2. In order to convert two substances, you need to create your own conversion factor based on the balanced chemical equation. So I see that we've got 3 and 3 for the coefficients of those two compounds. And so that's what I'm going to write down here. Since we want the CO2s, I'm going to put CO2 on top and 3Na2CO3 on the bottom. Sorry, my 3 looks terrible. Now, of course, you can tell that 3 over 3 is 1. So why not just write 1? Well, it's a lot easier for both you and I to check your work if you leave it as 3 over 3, because there's traceability back to the balanced chemical equation there. So I do strongly recommend you don't take that calculation and do it prematurely. We now know how many moles of CO2 we have. While this is technically sufficient to find the limiting reagent, I would recommend that we convert this into the molar mass and the grams right now, because we'll need that for the theoretical yield calculation at the end. So I'll multiply this now by the molar mass of CO2. To find the molar mass of CO2, we take the 12 for the carbon plus 16 plus 16 for the two oxygens. And so that should be 44 grams per mole. Moles canceled with moles, and that tells me how many grams we have. We'll come back and finish that calculation in a second. Now what I want to do is figure out how many moles of CO2 I can make from the phosphoric acid. Now, I've given you guys a little bit of a trick here. Not a trick, it's just a different approach to this, because we have milliliters of a concentration of phosphoric acid. This is how it would be presented in the real world, because phosphoric acid is always in solution, but it is going to be a little bit of a different calculation because we're not going from grams to moles now. What we're going from is milliliters to moles. So I'm going to start with my 13 milliliters of H3PO4. Again, that's phosphoric acid. I'm multiplying this now by what? Any idea, William?
I want 2 grams, moles over grams.
So let's think
Wait, I
about.
want to convert it to liters, don't I?
There you go. Yeah, yeah, yeah.
Yeah.
Because we
All right.
have milliliters, so I need liters in order to make use of this big M here. That big M stands for molarity, which is a concentration in terms of moles over liters. So big M equals moles over liters. And so it's just another conversion factor. I strongly recommend you actually cross this out and rewrite it as moles over liters when you're doing your work, whenever you're reading one of these problems, because it helps you remember how to use it. To convert between milliliters and liters, what I want to do is put 1 liter on the top and 1,000 milliliters on the bottom. Mils cancels with mils, and that'll tell us how many liters of phosphoric acid we have. Then I need to use my molarity term. So I want to put moles on the top here, and we had 1.015 moles. That makes liters canceled with liters. And now I do have moles of the phosphoric acid. So it's not always necessary to figure out what the molar mass of a compound is, because sometimes you can find moles without that information. It's always should be taken on a case by case basis. Okay, William, what should I do next?
Um, I you have moles over liter. Wait, no, you just have moles now.
I've got moles of phosphoric acid.
Um, and in that top part, you have grams.
Yes, I've got grams of what?
Grams of CO2.
Yes. So I need grams of CO2 down here as well.
So
But I
now you're
have,
gonna set up your conversion.
there it is. Yes. And what is the ratio I should use?
I want my PO4 to be on the bottom,
Sure
or
do.
H3PO4 on the bottom. So H3PO4 on the bottom, and then I'm looking for CO2. So I want um well this is CO. Is it the CO3 now?
No,
CO2,
it's
sorry.
CO2 because you have a conversion that goes between the H3 of PO4 and the CO2, right? It's this same equation
Yes.
up top.
Right, right.
And so what coefficients should I use in front of those two values?
Um, you should use a 2 in front of the H3PO4
Yep,
and then a 3 in front of the CO2.
you nailed it. Great job. Okay. And now what's the last step? So I've converted between my H3PO4 and CO2. My units are now in terms of moles of CO2. And so how do I get to grams from here?
I need the molar mass
Yep,
of CO2.
which is
It is going to be roughly 12 plus 32.
yeah, plus 32.
Uh 12 plus 32, 44.
Yep, you got it.
Okay.
And of course, because you were working diligently, you didn't see me circling around the 44 grams per mole that we already used.
No, I didn't see that.
And that's all right. But yeah, the good news is that sometimes you can reuse some of those calculations. And in this case, we have already calculated for the CO2 44 grams per mole. Good to know. You checked my work and I got it right earlier. So 44 grams over 1 mole there. Good stuff. Moles cancel with moles. And now we are fully equipped to figure out which one of these things is the limiting reagent. I'll take 15.5 divided by 105.8 multiplied by 3 divided by 3. This is the part where you don't necessarily need to stick it in your calculator because that's 1 to 1. And then at the end of all that, I'm going to multiply by 44. And I find that if, big if here, this is the limiting reagent, then we should produce 6.446-ish grams of what? CO2. Now we're going to go ahead and do the exact same process on the bottom, just solving for my math here. 13 divided by 1,000. Then I'm multiplying that by 1.015, and then I'm multiplying by 3, then I'm dividing by 2, and then I'm multiplying by 44. And here I got 0. Oh, come on back. Okay. Here I got 0. Did it again. Gotta debind that button. 0.8709-ish grams of CO2. So, a couple of questions now. Which one of these two reagents is the limiting reagent?
Um, is it the H3PO4?
Nailed it. Phosphoric acid is the limiting reagent because it produced less CO2. So it is limiting the amount of CO2 we can produce. Now, which one of these two quantities of CO2 is the theoretical yield?
Um, it is going to be the bigger number,
The smaller
6
number.
point, sorry,
That's
smaller
all right.
number.
Yeah. Because in theory, you can only produce 0.8709. You can't make more than that. And so if everything goes perfectly, that's the amount you will make. I like to use the grilled cheese analogy for anybody that hasn't heard me use this analogy yet. Let's pretend that we have 5 slices of cheese and a loaf of bread with 20 slices of bread. Now, you know that to make a grilled cheese, you need 2 slices of bread, 1 slice of cheese. And so, with my 5 slices of cheese, I can make 5 grilled cheese sandwiches. That'll use 10 slices of bread. Now, in a perfect world, I'd have more cheese and could use the whole loaf of bread to make my 10 sandwiches. But I'm limited to making 5 sandwiches because my cheese was limiting the amount of sandwiches I could make. And so the theoretical maximum is 5 sandwiches because of the 5 slices of cheese. Okay. Um, so that's my theoretical yield. That answers this question. And the final part, if the percent yield is 39%, what is the actual yield? So in order to solve this one, we just need to do one more quick calculation where percent yield, I'll write it over here, percent yield is equal to the actual yield over the theoretical times 100. The actual yield will always be less than your theoretical yield because in reality, everything sucks. It's always a little worse than you want it to be, right? Then we're multiplying that value times 100 because it's a percentage now. So we have the theoretical yield here. I'll put that on the bottom. We have the actual yield given here. I'll put that where my percent yield goes. And so 39 is equal to the actual. Yeah, I'm just going to call this x. It's a little easier to write. Divided by the theoretical, which is 0.8709, and that's times 100. So 39 divided by 100, and then times 0.8709. That's going to give me a theoretical, or sorry, an actual yield of 0.3396 something or other. All right. You thought we were done, but there's one more tricky part of this question, which is how many sig figs? What do I actually report as my actual yield?
Um, is it 3 sig figs?
So I'm going to look up here and I see 3 sig figs here, right? How many sig figs are there?
Are you showing me something with your mouse? Because I cannot see
Oh,
it.
you don't see the little dot on the screen
I do not
when I
see
do
it.
that? Oh, how funny. Okay. Good to know. Maybe I'll switch to a laser pointer. Let's see if that shows up. Oh, can you see this?
Yes, I see that. It's
Ah,
just very, very small.
okay, I see, I see. So
Okay.
that one right there, that guy has 13 milliliters,
Yes.
and so
Hmm.
that's 2 sig figs,
Two
right?
sig figs. Yep. I'm
And
with
so
you.
we just need 2 sig figs then. Okay, cool.
So is that, yeah, 0.34.
You got it. Yeah, that would be the final answer. Okay, and that's like 5 questions rolled into one. So hopefully a good kind of top-down overview of what could be expected on the exam.
But not that question.
Oh God, no. Oh, are you kidding
Yes.
me? It took me half an hour to solve it.
For all you listeners out there.
Yeah. I think we'll probably stop the recording at that point. That was a pretty good review of that.